Heat waves, drought, tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world.
Hello, everyone, and welcome to this episode of the Virtual Classroom series. If you're new to the Virtual Classroom, the way that this program works is we have a recorded video put online every week, followed by a live Q&A session with myself or my fellow education observer, Francis, where you'll have the opportunity to ask any questions you might have from the presentation or any questions that you might have about life here at the observatory or about meteorology. Today's episode focuses on fronts and air masses. So let's just jump right in. So in North America, we have a few different air masses that rest over different locations. And we can say that these air masses are semi-permanent, meaning that they kind of stay in the same location. They shift occasionally depending on the seasons, but they more or less stay in the same location. And they have different physical characteristics, such as temperature and moisture. They get these physical characteristics based on where they are located. So you're probably wondering what all of these different letters mean when they're resting in these different air masses. So the C means continental and dry. So these air masses originate over places such as the Western United States or Canada, or up here in the near the pole. So continental and dry. So it's not that wet. And they rest over the land masses. We have maritime air masses as well, and those originate over the ocean. So we have the maritime air mass down here in the Gulf and in the Atlantic Ocean, and then we have the maritime air mass over here in the Pacific Ocean. So we can classify these air masses further based on their temperature. So we have the Arctic air mass, which means very, very cold, and this originates over the North Pole. And then we have polar air masses, which again are cold. They're not as cold as the Arctic air masses, but they're still very cold. And these originate kind of closer to the pole, but not quite there. We also have the tropical air masses, which originate closer to the equator, so down here. And when we combine these air masses, we get the maritime tropical, the continental polar, the maritime polar, the continental Arctic, the continental tropical, maritime polar, and the maritime tropical. So we can classify these further, but these are just the easiest ways to kind of designate where these air masses rest. So since they have different characteristics like temperature and moisture, they don't really mix well. They interact with each other, but they don't mix well. And this is because when air masses have different temperatures and moisture content, they have different density. So density is a concept that's kind of illustrated right here. Let's consider that these are two air columns, meaning that this air is taking up the same amount of space. The only difference is this air is cold and dry, and this air is warm and moist. So we're going to think of each of these little dots as either air molecules or water vapor molecules, which are these squares that you're seeing. So in this air mass, you can see how there's a lot more air molecules concentrated in this air column, whereas in this air column, there's a lot less air molecules taking up the same amount of space. So we say that these air columns have different densities. And this is what kind of keeps the air masses from mixing and kind of what drives the interactions between these air masses. So if you're having trouble visualizing this, we can kind of think of different air masses as a lava lamp. So you might have seen these around, but this is a good representation of how air masses interact. So notice how each of the little blobs kind of come together every once in a while, but then they separate again. They don't really mix. So you can think of each of these little blobs as a different air mass. Again, they can kind of come together and interact, but they don't really mix. And that's because they have different densities. So when air masses move around, like I said, they're semi-permanent, so they kind of originate over the same locations, but they do shift every once in a while, and depending on the season, they may shift more or less. But when these air masses move around, they are separated by what we call fronts, like frontal boundaries. And these are a few different types of frontal boundaries. We have a cold front, a stationary front, a warm front, and a dry line. So now the weather on either sides of these fronts can be very different. So let's consider the cold front first. So cold fronts move in the direction that they are pointed. So this one would be moving this way. And the weather on either side of this front is going to be very different. So on this side, it might be really, really cold, like 32 degrees or something like that. But on the other side of the front, it's going to be a lot warmer. So it might be, let's say, 50 degrees. And that is also true for the warm front and the stationary front. The only difference is the stationary front is kind of stalled. It doesn't move a whole lot. And it takes a little bit more energy to get it to start moving. But the weather conditions are still going to be a lot different on either side of that front. The warm front, just like the cold front, is going to move in the direction it's pointed. So this way for this one here. And the temperature on this side would be colder. And the temperature on the other side, again, would be warmer, like 50 degrees. Okay, so the dry line is a little bit different than the warm front or the cold front or the stationary front because it separates air masses based on their moisture content, so how much water vapor is in them. And these are typical across Texas and the rest of the Midwestern United States. So on this side of the dry line, we might have like 50% humidity. But on this side, it might be much higher, say 90% humidity. And again, these are really typical over the Western United States, and they don't really show up in any other locations across North America. All right. So this is what the fronts and air masses look like on a weather map. So when we forecast the weather, looking at different air masses and how they're moving can help us a lot on determining what the weather is going to be like the next day. So if we are located, so let's say we are located right here, little person right there, we can expect that this front moving towards us is going to make the temperatures be a lot colder the next day. Whereas if we were located right here, we can expect the warm front moving over us in the next day or two, and our temperatures are going to warm up a little bit more. Okay. So let's look a little bit more closely at the structure of a warm front and a cold front on the next slide. So warm fronts, like I was saying, the warmer air has less density, so it kind of moves up and over the colder air at first. And then typical weather that's associated with these warm fronts is a temperature increase. So if you were right here, you can expect the temperature to increase. We can expect the humidity to increase, and we can also expect some drizzle and some light rains occurring on that frontal boundary. All right, so next let's look at a cold front. So cold air is more dense in nature than the warm front. Remember that slide that I was showing you with the air molecules? The colder air just has a lot more density than the warm air. So it kind of pushes the warmer air up and the cold air moves in below. So air is forced upward on the colder front boundary. So if we were located right here, we can expect the temperature to decrease. We can expect the humidity to decrease because air associated with cold fronts is typically drier. And we can also expect thunderstorms along that frontal boundary. So now let's look a little bit at how air masses interact. So I mentioned earlier, they don't really mix too well, but they can interact in very large, significant ways. So I'm going to try to draw some pictures here. Let's see. So notice that we have our cold front and our warm front. So this is what a mid-latitude cyclone is going to look like. And these are storms like winter storms. So for example, on this side of the frontal boundary, we might have some sunshine. Let's see. We can expect a sunny day back here after that cold front moves through, but we can also expect it to be pretty windy. So this looks very different than what it might look like in this sector of the warm front, where it's going to be warmer temperatures. This side is going to be much colder. Right here is going to be warm and very humid. And we can also expect some thunderstorm activity as well right here. So let's draw our little thunderstorm. Go. So again, this is where it's going to be warm and humid in this mid-latitude cyclone. So if we were to move over to this location, this is where the warm front is approaching. So we can expect it to be cool because that warm front hasn't moved in yet. So it'll be cool, and we can expect some clouds, and we can also expect some freezing rain. Excuse me just 1 second. Okay, we can expect some freezing rain in this sector, along with those cooler temperatures, but we will expect them to warm up as it moves in. 1 second. All right, now in this sector, this is where our most interesting weather is going to come up. We can expect it to be cloudy, again, just like in this sector. However, our precipitation is going to be much different. It's going to be in form of snow. So this is where our heavy snow showers are going to be located on the mid-latitude cyclone. So to just kind of summarize what I've drawn for you guys here, we have sunny, cold, windy conditions over here on this side of the cold front. Here we have warm, humid conditions and thunderstorms that can also sometimes develop into severe thunderstorms. On this side of the front, we have cloudy conditions and freezing rain. And then over here, we can expect some heavy snow showers or some heavy snow to occur as part of this mid-latitude cyclone. So this is what it might look like on a weather map, but now let's move over to how it looks in real time. So this is a satellite image from a mid-latitude cyclone moving across the United States. As you can see, there's lots of clouds associated with it, and we can expect the cold front to be somewhere along here. And then we can also expect the warm front to be located in this sector. So these are really, really big storms that can traverse across the entire United States that can affect a lot of different people. Where if you're down here, again, you'll expect some thunderstorms. If you're here, you can expect some clouds and some freezing rain. And in this sector, you'll expect some snow. So lots of different things associated with these storms. So let's look at another way that these storms might interact with one another, or with how these frontal boundaries might interact with one another. And this is kind of similar to our mid-latitude cyclone, but this is on a smaller scale for a thunderstorm. So now what you're looking at is a thunderstorm kind of growing and moving across the surface here. These clouds that you're seeing are the cold air rushing down from the top of the thunderstorm and moving across the surface and interacting with the warmer air that's located around it. So it kind of acts as a mini cold front, just like I was discussing, but it's just on a smaller scale. Again, this will be the colder air, some lightning, and then the warmer air would be located around it. Okay, so let's zoom back out into a larger scale. So you might have heard of some wind patterns known as jet streams, and this is another consequence of those air masses interacting with one another. So we might have some, like if we look at our semi-permanent air masses, again, we can expect some colder air up here, and then we can expect some warmer air right here. And what happens is air and wind kind of move parallel to these air masses. So we get winds that move this way, and this is what's known as the polar jet stream. And then we can also get winds that move this way down here, which is the subtropical jet stream. So the winds are kind of further emphasized in between these air masses up here. They occur high up in the atmosphere. And again, they're just narrow bands of elevated wind speeds. All right, so let's summarize some main ideas from fronts and air masses. Again, knowing where these air masses are going to move and where they're located can help us forecast the weather. We can describe air masses by their temperature and water content, and this in turn gives them different densities, so it kind of affects how they move and interact with one another. Whenever air masses move around, they are separated by fronts, and we have several different kind of fronts, including warm fronts, cold fronts, stationary fronts, and dry lines. And we also just saw that air masses can interact with each other on both small and large scales, or large scales being mid-latitude cyclones or jet streams, and smaller scales being thunderstorms. All right, and that's all that I have for fronts and air masses for today's virtual classroom. To register for our Q&A session for this virtual classroom, or to view more videos, you can visit our virtual classroom webpage at this link. And remember to submit questions when registering through Zoom, or email them to myself at abranton@washington.org. So let's just take a look at our webpage real quick. This is what our education webpage looks like. And this is where you can register for that Q&A session and to view more virtual classrooms. So thank you so much for joining me today, and I hope to see you in our upcoming Q&A sessions. Have a good day.